¿Qué tal? Muy buenos días a todos. Bienvenidos a la cuarta y última jornada.
Good morning, everyone. Welcome to our fourth and last day for CyberCamp 2018. We're starting the day today with the winner of the Spanish seminar on cybersecurity research. They were the winners of the last edition. And INCIBE organizes that seminar with them because INCIBE very much believes in the need to do R&D and I. And Mikel Iturbe is here to tell us about how to detect security attacks in industrial networks and why that environment is different from others. He is a lecturer at the University of Mondragon. A warm round of applause for Mikel. Thank you so much, Jacobo. Welcome. Thank you very much for coming to my workshop. And Jacobo has very kindly introduced me and told you that I'll be addressing how to address security attacks in industrial environments from my own viewpoint, in my own experience. Because in my research, I've been trying to compare how we've been learning about security from different points of view in different environments. And I've been looking into all of that for my PhD dissertation. I will start my presentation, tell you a little bit about our research group. I will tell you why industrial environments are different from IT environments. I will also tell you about different contributions made over time about industrial environments and cyber attacks. We heard about Stuxnet, and things have changed very, very much since then. And I will finish my presentation with some resources and guidelines for those who want to start research about cybersecurity in industrial environments. We're very fortunate now because compared to what was available 5-6 years ago, we now have quite a lot of tools and resources. So if you're keen on this particular topic, I will be pointing out where you can look into it. I hope we'll have time for a Q&A session at the end of my presentations, but please, I encourage you to stop me and ask any doubts. I want this to be interactive. I would like to hear your feedback during my presentation where needed as well. So let's get started. As you know, my name is Mikel Iturbe. I am a lecturer and researcher at the Data Analysis and Cybersecurity Research Group at Mondragon University. So that's what we do. We analyze and try to secure data in industrial environments, trying to solve issues connected with manufacturing problems, modeling part where, how to use less power in manufacturing, detecting attacks and intruders, consultancy for best practices about how to better secure industrial networks, and so on. Apart from that, I'm also a member of the Euskal Hack Association, which is the association we have in the Basque region on IT security. And we also organize our own conference at the end of June every year. So what is it that I do specifically? I did my PhD on industrial intrusion detection, and I was very lucky because I was given the first award, the first prize at the JNIC seminar this year. I work with cybersecurity, as you know, in industrial environments, but in fact, in our group, we always try to be very, very close to companies, whether it's industrial firms or cybersecurity companies. And here we can see up on the list, on the screen, a list of recently. I also work with data analysis in industrial firms, although that takes up less of my time. Preparing this workshop, I thought we should first cover a brief overview of some of the industrial attack detection approaches from an industrial point of view, as I said. When I started my PhD, things were pretty different. It's an area that's much more mature, that has matured very fast in the last few years. So before we get into the nitty-gritty of this topic, what is it that I mean when I talk about industrial environments? Are you familiar with this or not very much? So what is an industrial control system? Well, I'm talking about systems that automate, control, and administer or manage physical equipment. So in a manufacturing plant, for instance, there is an industrial control systems. So we're talking about PLCs. Well, we'll see about that later on. So when we talk about critical infrastructures, well, those are the ones we need for our daily use of power and transport, critical manufacturing, and so on. A lot of that is automated. Processes connected with power generation, for instance, that's all automated. So they've got these industrial control systems that's very much under control. Automated controls. And why is that special or different? Because the main objective of control systems is not keeping something very confidential, not at all. Their main core objective is for the process to continue to work. For instance, in a thermal power station, the main point for those systems is for the power station to continue to produce energy no matter what happens. Their second objective has to do with the real interaction these systems have with the physical world. So any problem that may arise, whether it's voluntary or involuntary, there are consequences in the physical world, whether it's intentional or not. There are consequences like people being left without power at home for however long, or a manufacturing plant not producing their goods, and maybe machinery being ruined because of that. So we have to be particularly careful in industrial environments. Problems don't just have cyber consequences, shall we say. They have real physical world consequences, and that's why security is even more important. So in industrial control systems, we talk about PCS, DCS, SCADA systems. There are different systems, true, but they're all fairly similar. So when we secure these systems, brands and names of systems doesn't matter that much. So I will be talking about industrial systems as if it was all the same thing. A distributed control system a DCS is different from a PCS or from a SCADA, but I'll be referring to them as if it was just one homogeneous single group. So what does an industrial network look like? Well, it's very, very much a vertical structure divided into very well-defined layers. At the bottom, we would have the process that needs to be controlled. That is hardware and physical environment and motor with sensors and whatever. All those pieces of equipment and devices and physical systems and hardware. So that would be the foundations at the bottom of that stack. Then we would have controllers getting information from the layer before so that they can then act and make machines do whatever. For instance, imagine we have a catering firm, a large pressure cooker making soup. So in that boiler or pressure cooker or whatever it is, if the temperature rises over and above a particular threshold, then the heat would have to come down. And that's what the controller is checking for it to work. We will see that the main control system in industrial environments are PLCs. What other control systems would we have there? Over and above that, in the same layer, we would have the SCADA controllers. It's like the supervising layer, because we have controllers down below in charge of less important tasks, and then the higher layer in charge of the more advanced controls. Then we have data historians gathering and recording all that information so that it's available for whoever needs it, whether it is to keep an inventory or whatever. And then we would have the human-machine interface, HMI, checking that the process is working on a higher layer. So we're talking about rather complex systems, mostly in critical infrastructures and facilities, which means that operators have to be supervising everything works correctly 24/7, non-stop. Operators, people who check if the PLCs, for instance, can't respond well to a particular threat, well, then operators would take charge and have control of the system, of the otherwise automated system. This is a PLC, which is the core of industrial networks. It's the heart and soul. They're in charge of first-scale control. This is not a new modern PLC. It's been working for a number of years. And look at all the inputs and outputs on that PLC. Well, they gather information from the field, then they're in charge of distributing information to the field as well, or for instance to open or close flows. All those actions would be done they would have Ethernet connectivity more and more these days, so that they can then communicate with the layers up above. But anyhow, PLCs are the main leading character, as it were, in this story. For those of you who are used to this type of hardware, well, we're talking about RAM memories not giga size, but mega size, with very limited processing power and very, very expensive, believe me. Why? Because they have to work in very harsh environments, surrounded by dust, in very harsh industrial environments, and logically we want to have them last at least as long as the production line is going to be operating. So I'm talking about lasting maybe a life of 10, 15, 20 years. Then the HMIs, human-machine interfaces, they're supervising up above that everything is working correctly. So that's a brief overline of how industrial networks work. So what happens if something goes wrong? And I'm not talking about science fiction, I'm talking about when things have gone wrong. What happens then? The first instance that we know about an attack to an industrial network, in fact, it's a little bit fuzzy. It was back in 1982. We're not even sure if it actually happened. It was an oil pipe in what was the Soviet Union still at the time. There was an explosion, and one of the hypotheses was that the software that controlled the pipeline, the oil pipe, was a hacked version, an illegal version of the original Canadian software. The American Secret Services said the CIA said a Trojan had got into that hacked version, and that's what caused the explosion. Although the second hypothesis was that it was human error due to an operator. And in fact, it's quite peculiar because we don't even have confirmation if the explosion finally and actually took place at all. Anyway, that's the first possible instance. Now, the second one, 2004, in 2004, this one did happen. A company that was in charge of wastewater treatment in Maruchi water breach. An employee stole some radio communication equipment, and in his vehicle he went to the different pumping stations, and as a result of that there was a spill of thousands of liters of wastewater into nature parks, and with no control. All that sewage. At that time, everybody thought that radio equipment was ever so expensive, so nobody would be able to do anything like this because of user authentication, security, but it did happen. He actually went round and opened the taps, the floodgates. He was caught, and the case went to court, and he ended up in prison. So, the third instance is the most popular example that everybody knows about, is Stuxnet, the Stuxnet incident. Apologies if I'm going to bore you telling you about this. Apparently, it's the most sophisticated malware ever written for zero-day vulnerability, affecting 2 power stations in Iran. The problem here is that the spinners, the centrifuge machines, were the uranium centrifuges, were working faster than they should have been, but operators didn't know about it. As far as they could tell, the centrifuge system was working fine until one day they just stopped working. They're very expensive pieces of equipment, and as a result of this, this was a big problem for the Iranian nuclear power plan and system. Then the following attack that was confirmed after Stuxnet was in 2004. It was at a iron and steel mill works in Germany. We don't know where exactly or which one. And in 2004, there was a spear phishing attack. An executive from the company received that email, and as a result of that, they got into the system, accessed the information system, and they had access to the furnaces. Well, there was a fire in one of the blast furnaces as a result of that, and that caused massive losses. The fire took a long time to be controlled. We don't know if malware was used. We don't know if that was their actual proper target. We don't have that information. We then move on to 2015, and this was the first large-scale attack to an electricity transmission lines. As a result of that, some 230,000 people in Ukraine suffered a blackout for a number of hours, with 30 substations switched off. Similar start, as far as we know, spear phishing on the IT network. And then that's how they accessed the OT network. Well, this is the first lesson we need to learn. We need to really clearly segment and separate the IT network and the OT network in a company. So, how can we protect industrial networks? What should the procedure be? Because most of us in this field of security are IT experts. So our idea is that we have to divide the network into different layers. We know that we think as IT experts that the main points there are data, confidential data. That's why they should be at the core of the protection. Then the following layer to be protected, most protected, would be the application, then the host or hosts, and then last but not least, the network. But for us, the core, our focus, what is it? It's data and data confidentiality. If you go to a company, to an industrial company, and you ask them, hey, what would you rather, not have access to your data for a whole day, or for the big wide world to know about all your data, for your competitors to know, and so on? Well, I can tell you, they'd rather not have access to their data for just one day in, non-industrial networks or non-industrial companies. Whereas if it's an industrial environment, it's the process that's important. What would be at the core would be the process. It's different from what we think as IT experts. They want to continue to produce their parts, nuts and bolts, whatever it is, and traffic, data, host, network is very much secondary for them. Why? Because it's the process that has added value for them. Because industrial cybersecurity, as opposed to IT cybersecurity, well, the cost of a cyber attack is very, very easily calculated. They tell you straight away, if it was 1 week, it would cost us this much. Whereas if it was an attack from an IT point of view, not an industrial point of view, it's much harder to calculate that. How much does it cost if the web line for a company crashes for a week? Well, if it's an online shop, it's hard to calculate, but in an industrial environment, well, they just count the nuts and bolts they won't be selling. That's the calculation. So again, it's process availability that matters most. The process must keep going and working no matter what. So when we prepare security measures, we have to be ever so careful and respectful not to compromise the process first and foremost. So again, what is the main difference between the industrial network and an IT network? Well, a number of differences, but first and foremost, in IT networks, we mostly care about communication and data processing, whereas in an industrial network is the process that matters. Manufacturing process, because let's not forget that security for a manufacturing plant very often means safety of operators or of people around them. Can you imagine how nice it was in the Ukraine when people had this blackout, thousands and thousands of people in the middle of winter, particularly depending what boilers and heating systems they have? It can't be nice, right? Another important feature in an industrial network is that timing is always shorter. Mostly if we're talking about the automotive industry or where PLCs are very much present, we're talking about 200 microseconds. That's timing for them. Whereas if we're talking about wastewater treatment or sewage treatment, for instance, well, time is important as well, a little bit less, but still very important. So when we deploy a new security system, we need to take that into account. We can't go and do sniffing with a man in the middle, and then that's going to cause some latency. That would add a few more microseconds in latency, and that would have a big impact for them in the manufacturing process. The timing. Industrial networks also have other differences and peculiar elements.
There we don't have users that go to see the newspaper early in the morning. All that traffic comes from PLCs, the ones saying to the control server, this is the temperature, so every every second, I don't care, it'll stay like that. And every now and then the operator will do something, but industrial networks are much more static and deterministic than the IT networks. Topology does never change, contrary to a Wi-Fi network where users log on and out at all times. It doesn't change almost ever, and that's good, because if we see something changing, it means that there's something there that is not as it should, and that's what I'm indicating here. And then what I said before, PLCs and the nodes as well. So computing power is minimum. And then we are using equipment that is way older than the ones we're used to. So what can we do? Let's try and use these features that industrial networks have trying to detect attacks. If they are so deterministic and static, let's dive into that and explore it. And this is the state of the art for attack detections. And let's say this from a personal point of view. Before StackNet, which seems to be the Pleistocene, well, things were being done and have been done. This was a field of research that was quite limited, contrary to what we have now. But things were done. And we are talking here about solutions that were already existing, such as ideas based on signature already on IT that were translated into the industrial world. But mainly, these were proofs of concept, and part of the standards and the good practices we have for industrial networks were non-existent back then. Whitelisting as we call it now, very much recommended, but was not that advanced. There were no industrial firewalls. We didn't have the network isolated from the IT world. It was kind of a proof of concept, but without a true need, a real need by the industry. Su and Sastry did indeed conduct a survey of the existing papers. That was 2010. And it summarizes all that had been done before Stuxnet. And they discuss some terms that will later on become more important. And that is model-based detection, which basically we built a model of what the network should be, or the project should be, in order to detect things that are out of the pattern, out of the model. And then specification-based detection, where we create some manual standards or rules stating that there are some things should not be as they are, which is a bit more simple than the model-based detection. This is before 2010. There are already some papers discussing it. There is a starting research field. There's a few workshops on the topic, but it is still a bit far from where we are headed. Then we have Stuxnet. Everything is on the media. People get scared, and it becomes a field of research that is a bit more fashionable than it was in the past. There's more on the topic, more workshops, and everything having to do with industrial cybersecurity. A bit unthinkable some 10 years ago. And so people start working on this seriously, but mainly two fields, which are network detection, attack detection. So I see how the network behaves, see if there are any packets that do not comply with the rules, and then field detection. So I don't check the network. I don't care about the packets or the flows or the services. What I'm interested in is knowing what's going on with the process. And if the process is not working as it should, that's what I care about. And so that's where, with the Stuxnet ambiance or setting, that's when I start my PhD dissertation. First of all, with my dissertation, I came to realize there weren't security visualization tools for industrial networks. So what we did was build one using string diagrams. That's the circle which indicates that there are several industrial hosts, and they're all arranged there. We have PLCs, that's blue, then HMIs, that's purple, and then control servers, that's orange. I said before that industrial networks are very deterministic. If a host is all the time communicating with another one, this will not change. If a PLC has one or two control servers associated, we'll only send information there. Doesn't need to send information elsewhere. The PLC is just an automated process that is producing the traffic. It will not go on the journal or the newspaper to see how the soccer team's done. That traffic will always be static. And we said, if it's static, let's go and see what about the network flows, which should be static as well, and that's what we did. Those lines connecting different parts of the circle are network flows. The width of those strings show the number of packets per flow, so the wider the flow, the more active the traffic. And the narrower the flow, the narrower the string. So what we did was decide to build a whitelist who is in contact with whom, and whoever does not meet the parameters, we will label them red. And that's what we did. See the flow between HMI and PLC where we should not have any traffic. And we see that is blue. This was done with a car painting line. It is a real example. And then as the reference, you will see some other use cases where we detect DOS. And it is not just the existence of abnormal flows or the non-existence of a network flow. If a PLC is offline, we need to know why, because that's also important. We don't know what's going on with the process. So that's it. And then, after having done this, there was a life crisis, as it usually happens with PhD dissertations. And there we changed our focus, not just at the network, but also what about the fields? Because the network, for IT people, this is a bit more intuitive. These are flows and packets, and these are things we're more comfortable with. When we go to the field, we are talking about temperatures, vibrations, pressures, so these are physical magnitudes, the ones that we are monitoring. These are a bit more complicated for IT, for industrial backgrounds. Well, that's easier for control. I mean, in the field, the shop floor. But for the network, sometimes the existing equipment won't allow to have many things. For example, network flows. For those, we had a mirroring of a switch, and that was doable because it was good enough. But most of the industrial switches back there is still operational now, but you cannot be used with mirroring. So what about flows such as S flow or net flow? These are top range actually. So when we talk about industrial equipment, which is expensive, by the way, it becomes even more expensive. So sometimes the network electronics existing is a bit more basic. So in the field, we know the data are there and we do monitor them. The operator monitors everything, temperatures and everything. So there's something going out that should not. So you don't need to buy expensive switches. You do have the information out there. We saw there were several papers based mainly on physical models. I have a process and I'll describe it using code, and I'll describe everything the process does. This is amazingly complicated. Collecting all the information from the physical world into code, it is actually so difficult because you see interdependencies and it isn't simple. It takes lots of expertise and it's costly. And whenever the process changes, the model is useless. So we focused mainly on attack detection, which would be data guided. We only get data. We do not build a physical complicated process that will not, yes, it would work, but it would be too complicated for what we want to do, as long as we can get that information out of the data. So first we focused on attack diagnosis. And why is that? There were already some interesting proposals in attack detection or anomaly detection, so to say, but oftentimes we didn't know, or operators didn't know what was going on. Something was wrong, they knew, but they didn't know why. So this is an example. So figure this is a pipe. And there's a fluid inside, and there's a flow sensor on the left side. If the flow is flowing, the sensor knows the flow rate per, I don't know, volume per hour or per minute, whatever. Right side and bottom side, we see two cases where there is nil. That's the flow rate. One because of the valve is closed, so it doesn't flow through. And the other one, for whatever the reason, there's a problem and it doesn't reach its destination. So with those two variables, so there's a drop in the incoming flow. So we need to know why. This is interesting. There's been an attack where someone tried to close that valve, or maybe there is a problem with the provider and we didn't get the raw material in. By checking these graphs, it's not doable. All the details are there, but basically, with a model with main component analysis and then also co-production graphs, well, we saw that for some conditions that was doable. With some graphs, well, on the left side you see there is a negative bar, which is a large one, stating that the incoming flow is lower than it should be. And on the right side, what we see is that the opening ratio for that valve is lower, way lower than what it should be. So it is closed. Interesting, isn't it? We can see if there's been a malicious attempt to close the valve, or maybe not. What's interesting is that it doesn't need to be network level. It doesn't need to be a command. It's maybe an operator who's tired, gone to the valve and manually closed it. And if we check the network level, we would not be able to detect it or diagnose it either. So this went on, and we had some other network parts integrated or embedded, but there is another more recent proposal. After my dissertation, this was published on CSS, and this was the detection of more advanced attacks in the field. This is PASAT, that's the name. Again, if you want the details, you can go to the paper and we can get a signal, whatever that is, a vibration, change in temperature, change in pressure, whatever. And with the blue side, you learn. And just like that, you build a cluster, which is green. And then, once we've learned, we see how it's doing. And the black side, the black part keeps producing, it's okay. And the black part of the dots are inside the cluster. That is the blue part. But as an attack starts, the structure of the so-called temporary series is changed, and the red spots or dots move to the left side of the cluster. That information is projected with just one variable, which is a detection variable, the one that you see on the bottom left side. And if the attack starts and it all changes, that attack indicator is spikes over a threshold, and we get a warning that is something wrong. All right? So we ran several attacks, a chemical process that I'll explain later, also a grey water treatment plant, and then a water distribution plant. On the left side, we see an evident attack, especially an operator that is checking the variable and can say, well, there's something going on here. But it is detected, so there is a spike in the signal and an alarm would go off. What's interesting here is the one in the center, the middle case. the red side, it's the attack, and it doesn't vary much when compared to the other graph. It is such a subtle attack that it is masked inside the signal noise. And the bottom graph, maybe you cannot see, but we've compared two methods. The black one, which is a previous method, and then the blue one, ours. And we see that the prior method cannot detect it, but ours can. The reason is that many of the proposals nowadays, what they do or used to do was knowing what the process status is now. Let's calculate or estimate. Let's estimate the next read. So we kind of predict the future, and then if the prediction and the reality look alike, no problem there. Many attacks that are so subtle that don't change much, we will not be able to detect like this. And so what we do, or what we've done, is try to see if there is any structured breakup as part of the temp structure, so that we see that in surgical detail. Then on the right side, we checked, because these were attacks that we performed on a lab environment, but we wanted to see whether they can be translated into a real plant. This was a water distribution plant. And yes, we saw that if there's something weird with the process, it doesn't need to be an attack, because we don't have any more information on the spikes. But still, we see that we do detect them. So, from before Stuxnet, this field already had some, there were some proposals, mainly that were IT-based, to detect attacks on industrial networks. Then they've used that specificity, that the deterministic nature of industrial networks, to detect those network attacks. And then lately, the network intrusion detection in the field, that would be the process level, is quite active. Where is this headed? Well, I guess this is my own forecast here. We will come closer and closer to machine learning based solutions. We will find more and more proposals using that information that we collect from the field for intrusion detection. And I feel they will be integrated with the network proposals. So if we see something wrong in the field or in the network, these will be fed back, and we will take actions on the network. And that's where I see the greatest potential for software-defined networks, with a central controller having all the network logics, and there it will face the attack in a dynamic way. But always with that touching or interfering with process availability. These would be otherwise secondary. What matters here is having process availability. If we can make sure that the process keeps producing, that's positive. If it doesn't help us with that, it might not be useful at all. So, if there's someone in the audience who likes this topic and thinks, okay, industrial security, I like it. So there I would like to discuss some resources that helped me back in the day. Now we have many more, but let me encourage you to use them so that you can learn. Especially from the IT point of view, we need to change our mindset. We need to play around and learn, and it takes effort. So read as many books as you can. There's two I've chosen. There are a few more, but on the left side, that's a classic. It's some years old, and it helps with research and also helped me learn what an industrial network is, how it behaves, etc. Right side, you see something quite similar. These are not books that explain where the field of research is now. That's not the goal. but it helps us understand what the problems of industrial cybersecurity are, why we cannot use an antivirus on a PLC, for example. PLC does not have enough computing power for that. But if you don't know, you don't know. These books help. Then for research, and mainly academic research, I would recommend this other book, which might not be so much focused on cybersecurity, industrial cybersecurity, but it helps us understand the language that is used in academic journals, false positives, false negatives, and all of that. I really recommend it. Then there is another, well, there's so many repositories on GitHub, I'll mention that, but first there's a list, a resource list to learn industrial cybersecurity, from the behavior of PLCs to pickups with network captures. It is good, have a look at it. It might help you find tools for industrial cybersecurity, some as grass modeling. I don't know if that rings a bell, but sometimes for service recognition or network recognition or host recognition, it is not advisable to use Nmap contrary to IP networks, knowing that there is something similar, not that intrusive, which is more passive. That's grass modeling and other 100 tools there. And then there's a couple of industrial processes. First one is a bottling plant. Virtual plant, that's the name. We have the process on the one side. That's the top left side. There's a tap filling a series of bottles all the way up to a level. On the right side, you see HMI, where it says the operator, how they're doing. And both communicate through a industrial protocol. And then there are some preset attacks that you can have with your own buzz attacks, and where you see that the bottling plant is not working, is not filling up the bottles. Otherwise, the plant would be flooded. And it's easy to see, it's Python, so easily understood. And as a first step, it's okay. And then there is a process, which is a bit more complicated, but I really like it. The chemical process, I said before, it is a real chemical process, this one. It is a plant that produces some chemicals. And here we're going to have these surgically accurate attacks. See the process, interdependencies. And actually it's complicated because it takes some learning about control theory, and it takes some chemical engineering as well, but it is such a powerful tool in order to drive attacks and also field detection. There's a framework where you can close valves, spoofing off sensor signals. Very good, but complicated though, and as such it takes time. All right? And just to finish here, so that you get a general idea, ensuring industrial networks is strategic. It is important because of the risk it entails and because of the cybersecurity features involved. But there are some specificities we need to consider. Some play in the favor of the cybersecurity researcher and some others against us. Solutions that are based on machine learning or artificial intelligence or whatever is a very active research field for the field and for the network both. I'd like to encourage you, if you want to learn, it isn't impossible. Yes, the mindset has to be changed and many things need to be learned, and maybe we IT technicians were not so used to it, but it is doable. I managed it, and so that means that I guess any of you could. That's been all. If there are questions, I'll be happy to take them. Sure. Microphone, please. My answer would be it depends. The top range companies already have wireless sensors and that kind of thing. That is a reality. Reaching out to those companies with more resources, but even smaller, more traditional companies where lines are not changed that often, there maybe it remains to be seen when and if. It is a very conservative sector, it's true. And the mindset would be if it ain't broken, don't fix it. So for the avant-garde companies, I think there is a change, but for other companies it might take longer. But yes, it's a reality, it's not sci-fi. Okay. Oh, there's one. What about security controls that should be implemented, the basic ones, that is, to safeguard information assets? I would say to monitoring network, because we don't know what's going on. We think we know what's going on, but oftentimes it is not the case. We need to see what's going on first, and segmenting and segmenting. Almost total segmentation between the control network and the IT network and the operating network. So all accesses are well controlled, because there will always be some access chain, because any remote maintenance and everything has to happen, but it has to be tightly controlled. And then as a plus, segmented inside the industrial network for different lines, for example, production lines or also business divisions. That all has to be very nicely segmented. These two I find are basic. And then some, as usual, it's not just technical, it is cross-sectional. Awareness raising and training of the people, the employees involved. And then monitoring. Maybe you've had an experience by using some kind of a tool. You mean off the shelf? Well, open source, or I personally haven't had. Some people in my group, yes, but I haven't. So I'd rather not say much, because probably I would mess it up. All right. Thank you very much then for your attendance. I hope you enjoyed it.